So let me put this on here. Uh, yes, but this is all good. So it's a healthy stream. Excellent connection. Sure. Uh, how it appears now? Is it okay in the stream? Because or should I use another setting here? Can you see how it is? It's not the full screen. No, no. This is. I think that it should be. So what I will do is this. So how it appears now? Well, how much is the delay? Oh, OBS.
Just wanted to
Yeah,
double
you're
screen.
sharing the screen.
This
Okay.
screen.
Try to change the video capture.
Window capture. So you prefer to use a display capture instead? This one, and then use it the second window. Yeah. So it's this one. This one you wanted me to use, and then I can use. I can put this in a presentation mode like this. So can you? How is it? Alt here. How is the completely dark? Oh, because of this one. Look at this. Good. Yeah, it is a full screen. It is a full screen. Exactly the one that this is, this is all because of you. So you recommended this. This is a full screen. So it's exactly 1-to-1 match. Thank you. And I'm going to be roughly here. So it's looking okay. The screen is not perfect today, but it is what it is because the lightning. Yeah, that's okay. That's okay. It's good enough, I would say. Okay. So I have 32 slides only today. So it's going to take less than an hour and a half. So I'm thinking that's going to take like 60 minutes perhaps. Okay. But the quality is okay. Seems so. So one thing that, can I make a final adjustment? So if we raise this up a bit, so then I'm sure it's going to look better than as far as the cable allows it to go like this. And then like little, yeah, it's much better. So get a little more up. Yeah, there, that's good. Okay, thank you. All right, 60 minutes, roughly 60 minutes today. Okay, so hey, thank you guys. The week ago, it was an interesting lecture about the bicycle dynamics, and I think at the highlight, I think at least the lesson I learned from that is that if you take any subject matter you want and you really fully focus on that, you can do a lot of stuff. So it doesn't necessarily need to be a fully, extremely complicated airspace application, but even a bicycle can do the trick for you. But you just need to make it in a certain scientific way. And that, I think, was the most significant lecture. Also, it was funny to see that so many errors is being made during the course of explaining what keeps the bicycle in upright position. Big question that is still not clear to me is what keeps bicycle to be in upright position. And that's actually is a set of equation that explains that the stability of the bicycle. So it's not as simple you might think that it is. So it's a complicated thing. I once thought that I can make a kind of like a common sense explanation of what keeps the bicycle upright position, but these 5 equations are quite complicated and the parameters are heavily mixed. They have a strong interaction with each other, so it's not that simple explanation. There's a quite complicated explanation. All right, so what we're going to do today and what we're going to do the rest of the course is follows. Today we're going to take a look at the fatigue analysis. So we learned already how is that we can extract stresses, strains and stresses from multi-body models. What we can do with this information? Well, the obvious thing is use that in a structural strength analysis. But multi-body system dynamics may not be that good in that particular application because you can do the same by using static analysis in finite element method. But what's difficult to do using finite element method is producing stress histories, where you have a stress information not just in a one single incident, but in a longer perspective, longer time-wise. And that's something that you can do by using multi-body system dynamics, and how that can be used in fatigue analysis that I'm going to explain in the beginning of today's lecture. Then we're going to move on completely different subject matter, which is a contact modeling. And the contact modeling is something that you're going to learn that it consists of 2 different steps. First is a contact prediction, that you're predicting whether or not there is a possibility of contact. And once you have predicted that there is a contact, then you can actually model the contact event itself. There is 2 possibilities: smooth dynamics and non-smooth dynamics. And these are the 2 basic principles. The smooth dynamics is something that is making awful lot of sense. I mean, it's simple approach, but it comes with the serious limitations. Non-smooth is conceptually more complicated, but comes with the certain advantages, computational advantages. So that's what we're going to do today. Then a week from now, next week, Wednesday, I'm hoping that we're going to get the last visiting lecture about biomechanics. The biomechanical applications, how the biomechanical systems can be modeled and analyzed, and what are the things we can do in the field of biomechanics using the knowledge we gain from mechanical engineering. And then the week after that, which will be already last week of this semester, this period, excuse me, I would like to give you like pretty much all the rest of the wisdom that I can offer to you. So I would like to give you a highlight about what next, what I'm seeing to happen in the field of simulation as a next step. What are the future perspectives, future hopes, future things that make sense to monitor, and that will be it. Yes, sir. Oh, yeah, that I will do. Will do. I will give you again a list of questions. Yeah, sorry that I don't have them with me today, but again, we have a list of questions. Then you can do the selection. You can select the one that you could definitely see in the exam paper, and the question that you're definitely not going to see in the exam paper. But again, questions will be offered prior to exam, well before that. So let me make sure that it's available next week already, so you can see what are the possible questions. And there may be questions about bicycle dynamics too, but they're not going to be too complicated. Something that if you follow the audience lecture, you definitely are able to answer. Okay, sounds fair? Sounds good? Yes. Yeah, that's a good question, because if I did my math correctly, there is 2 more weeks to go in this period, correct? All right, so let me take a look at my calendar. So the week. So are you guys following the week numbers, or should I give the week based on that Mondays? So if I say that, so let me see. So this is week number 5 in this period, correct? All right. And today is a week number, what is it, 14th. Okay, so next week is a Monday, 8th of April, then the Monday, 15th of April, and the week after that, which is 22nd of April. Monday is the 22nd of April. That's going to be the exam week. Is that okay? Because then there's going to be 2 more days left in April, and then 1st of May is our Wednesday. What is it? 4 weeks from now. And that's my understanding is that most of the courses are done, completely done by that. Exams and everything is done by end of the beginning of the May, end of the April. Is that correct? Something like that. Something like that. Hey. So yeah, and of course the big deal is it is a Labor Day, this 1st of May. All the students would like to have a party day before. So I understand you guys are busy that week. So let's make sure that everything is completed by end of the week, which is a Monday, 22nd of April. Sounds good? Sounds good. Isn't it available already? Should it be available? Because we created that already. So can you check it? So probably it's available in Moodle. In Moodle. So can you take a look at the Moodle page? It should be available. Yeah, that's a good question. So where exactly you can find it in Moodle, that I don't know. But it is. We checked them already sometimes back, and all the grading is already in this Moodle system, directly in the Moodle system. Can you see it? Or maybe there's a button that we need to click to make them visible for you. I think that it is made it. Am I completely wrong about that? Okay, all right. So let me figure out. So we did the creating, but it's not visible. Can you see not yet created? That I don't believe it because I knew this. Because the part of the exam creating was my responsibility, and I did that. I know that is made, but maybe we need to make it somehow visible for you. Not created. All right. Okay. So I don't want to play Moodle that there's a technical mistake in the Moodle because obviously we did something incorrectly, but the numbers are there. We just need to be able to show it to you. How? That's a good question. So we need to figure that out. Magic button to make it visible for you. Okay. All right. Anyways, so let's get started by summarizing what we discussed week before we met Arend. So let me take again. It was a what was it? Alt tab. Yep. No, still not. Yep. Like this. Good. All right. 2 weeks back, we discussed about how to describe these ways that the structure can deform. And we learned that the way to do that is based on eigenvalue analysis. And eigenvalue analysis is telling you a lot about the structure itself. It's not about the responses, but what are the features of the structure. And these features are coming from the combination of mass and stiffness, nothing else. And that's why everything you get out from the eigenvalue analysis are not absolute values, but they are just the properties of the structure, nothing else. This is good to keep in mind. Eigenvalue is a property of the structure. Eigenvector, the way it can deform, is a property of the structure. It's not a response yet, because the properties are coming when we are assuming that the externally applied forces are set to be equal to 0. So the forces are not in a play when we are conducting the eigenvalue analysis. That's why it's all about the structural behavior, structural properties. And that's we need when we wanted to model flexible bodies in a framework of multi-body system dynamics. Problem when we're conducting the eigenvalue analysis is to set the boundary condition, because the boundary condition has a different nature in finite element modeling and the multi-body system dynamics. And in general case, it becomes to be complicated to find a proper boundary condition. Actually, it's a very challenging task to do it properly. And to overcome that drawback, there is a method that is often used in a commercial software. And this method is called Great Quantum Method. And it is giving you a waiver from thinking. So that's basically what it is. So you don't need to worry about that much about what is a proper boundary condition. But instead of doing that, you're just selecting the points that you're interested in. And these points that you're interested in are typically the points that the structure is connected to neighboring bodies, or there's a force, typically a pin force, applying in this point of interest. All right. So you can select as many points of interest you want. And once you make your selection, then everything after that will be automatically organized. An automatical procedure after that is such that the point that you click as a point of interest, those will be selected. I mean, each of the degrees of freedom associated those points, not allocations, will be selected as a boundary degrees of freedom. And the rest, which is typically more than boundary degrees of freedom, are categorized as interior degrees of freedom. Then what happens is that this finite element software is automatically reorganizing the mass and the stiffness. And based on the reorganization, is computing two sets of deformation modes, two sets or two different sets that describes the way the structure can deform. And these two sets are static correction modes and the modes that are obtained by using the naked value analysis. So they are described here in this algorithm located in our upper left corner. So first set is that you're setting this point of interest fixedly attached to ground, and then you conducting the naked value, seeing how is the rest of the degrees of freedom, meaning interior degrees of freedom, how is that they values, how is they are vibrating when you keep the boundary degrees of freedom fixed. This is the first set of modes you can get. Second set of modes is a static correction modes, where each of the boundary degrees of freedom you impose the unit displacement one at a time. That's another set. Problem, minor beauty problem. This is not very significant in my mind, but some people feel that this is not good and they cannot live with that, is that the static correction modes are not orthogonal, mathematically orthogonal. So what's the big problem if they are not orthogonal? Well, the big problem is that when you use them to compute the reduced size of stiffness and mass, result is not diagonal. That's the only drawback. So is that a serious? I don't think that it is. I don't think that it is, because what matters more than the diagonal shape is the reduced size. If you can come down from, let's say, 100,000 degrees of freedom to 20 degrees of freedom, that's what really matters. Not so much about the fact that your mass and stiffness is not diagonal. But anyways, there is a way to solve this minor beauty problem, and the minor beauty problem can be solved by using the Munster terminology or the technique that is called orthonormalization. So what that means, so what is an orthonormalization? You take your two sets, you combine the gadget, you're comparing the new reduced size of stiffness and mass, and using the reduced size, stiffness, and mass, you are conducting another eigenvalue analysis. And then everything for sure is orthogonal, because if you do the eigenvalue analysis, then for sure the modes you can get are definitely orthogonal, meaning that they have no dependency with respect to each other. So they are completely independent. Right, when you do that, you can kind of mixing all the modes. So they are no longer having this feature about fixed interface normal modes or static correction modes, but they becomes to be something that is more chaotic. And something that is more chaotic is that they have roughly three free modes, and then they have these boundary modes. The boundary modes are very local deformation associated to point of interest. Anyway, so that's what you can use. And now this is something that are orthogonal. So once you multiply your stiffness, now reduce size, stiffness, and mass, you can get the diagonal representation. That's end of the story. So that's how it goes. So, okay, so hopefully this noise is not bothering us too much. Then we learned that once you have a flexible body, you can get the information about the strains and stresses as a post-processing procedure. This is post-processing procedure, because what we're computing in a multi-body system dynamics is first we're computing these modal coordinates. Modal coordinates multiplied by corresponding modal matrix gives us a nodal degrees of freedom. Nodal degrees of freedom, or let's say nodal displacements, are not yet strains or stresses, but we can use them to get the strains and stresses. And there are two alternatives to make it happen. So we can use the model, let's say kinematic matrix that is coming from finite element method, and using that information, we can automatically get the strains and stresses in multi-body software. Or more complicated, we can take all the forces we obtain during the dynamic simulation, take them and extract them, use them in a finite element software, and have a multiple load cases. And using the multiple load cases, we can produce a deformation again in finite element modeling. Very complicated, not recommended to use it, but still sometimes used, because the second one, which is based on this modal stress matrix, which needs some information about the kinematic matrix, sometimes this information is not available. Why? Well, because typically a commercial software is used to make this all happen. And in a commercial software, they may not give this information openly to users, because the kinematic matrix is something that is typically in the numerical forms, or not that easy to deal with, so you might not get it. And if you don't get it, then the only choice left is option number one, which is kind of ridiculous, that you compute the dynamic equilibrium, and based on the dynamic equilibrium, you take all the forces, that's external applied forces and inertial forces, put them as a load cases in a finite element software, compute the deformation again, and now you can get an access to strains and stress. So that's how it goes. Okay, so what we can do with that? Well, then we can create these stress histories. And stress histories we can in turn use in finite element fatigue analysis. And like I mentioned 2 weeks back, fatigue is a statistical thing. So we can get probabilities about how large percentage of the details will last in a loading history like this and that. So it's not that we can definitely tell that, you load this in 10,000 times, and for sure this is going to be a fatigue crack damage, large enough that the structure will fail. That's not going to happen. But certain percentage of the structure similar than what you are looking at will get this damage. So this statistical play all the time. This is good to keep in mind. Fatigue is a big problem, particularly when you're welding structures together. And there are two big reasons for that. Actually, there are three reasons for that, but two major reasons. And the first major reason is that because of the welding process itself, you can introduce an initial crack to welded toy. It's not going to be very big, but it's going to be something that for sure you can have an initial crack. And this is because the welding process itself is not ideal process. And when you take a close look, very close look about welded toy, for sure you can see something that is not perfectly made. And these act as an initial crack. Now this actually is something that if you want to improve the fatigue life, if you want to make a fatigue life longer, the way you can do that happen is that you can go after the welding process and you can use a different kind of post-treatment processes with the welded toy. And the options are hammering. They are like mechanical hammers that you go after and you hitting this welded toy mechanically. So it's like some kind of the device that hits this welded toy, try to kill these initial cracks. You can use TIG welding that you can go after. Once the welding process itself is made, you can go after the TIG welding and try to make this initial crack to disappear. Big problem is this, that most of the welding, when you look at this typical welded structure, there is meters after meters, maybe kilometers after kilometers welding, and becomes to be heavy to go after and try to fix each of these details, because each of the details, each of the millimeter can be potentially risk place. And this what needs extra careful to make it happen as a post-treatment procedure. But that's a possibility. It's a possibility. Okay, so initial crack, one big problem. Another big problem is a high residual stresses, which I'm going to explain to you momentarily. And one more problem is that typically this is not as big problem that two first ones. Typically, the welded joint is located in a place that there is a high local stress concentration, because typically there's there is a two plates like this. This is a typical case where there is a local stress concentration, which increase the loading and stress history in this particular location. That's very, very typical case too. Okay, but when you're welding components together, it's all about the crack propagation. It's not about the crack initiation, because non-welded structures like engine parts, if you see a crack, for sure it's done. So the fatigue life remaining is not much. Whereas in welded structures, even when you have a brand new structure, you can make a fair assumption that there is initial cracks in your structure, and now you just need to control that the crack propagation, the crack drawing, is not going out of the hands. Okay, makes sense. All right, then I have an in-class quiz next, and we will get back to this. In welded structure, this is going to be, it's not going to be on yet, but I will put it on momentarily. So welded structures, the fatigue life is dominated by. The dominating factor is crack initiation, crack propagation, final fraction. Okay, this is easy. Okay, so you guys want to answer already? Let me see, Alt, Tab, and I will go, okay, I cannot do it because I don't have a browser open right now. No, I do. Alt Tab. Oh, this, by the way, this is really convenient to do this way. Streaming is keeping healthy all the time, and I could do my stuff in the background. This is really nice. Why did I figure this out earlier? Okay, this is going to be the thing that I'm going to do next year, next academic year. This, this thing that, I keep this, switching back and forth in this overhead projector is a big pain, but I don't need to suffer this anymore because I'm going to use this new technology. So, all right, so the Socrative is on. So let me do it as a teacher. All right, so you can answer if you're ready. And I will take myself back to this guy here, this guy. All right, so I'm going to revisit this slide momentarily, but Socrative is on, and room is LUT2, by the way, not LUT. So you were able to find it? Good. All right, so we'll get back to that momentarily. Okay, the problem about this residual stress is this. This is this famous strain stress curve. And you know how the steel material, aluminum material, how they perform. They perform in a way that there is when you get started from the origin, I mean, zero strain, zero stress, and you started to increase the strain, which is displacement in a sense. You see that the stress is increasing, and it's increasing linearly. And once you get your loading away, the structure becomes to be back where it started. So this is an elastic deformation. And elastic deformation is most common thing that happens. Now, very locally, again, let me emphasize, very local, when you're not looking at the structure as a whole, but you look at the minor detail in your structure. Due to the welding process itself, because you're introducing so much heat when you're welding components together, you have very high residual stresses. Actually, is in a corner where this linear behavior turn out to be non-linear behavior. And this non-linear behavior is very bad because this is something that if you step away, let me rephrase it. If you step left from the point that you can see there's a green pot or green spot in my screen. If you step away from that, then you can introduce a permanent deformation. And again, now if you have a high residual stresses, you can introduce a permanent deformation locally. And this is the situation when you have this conventional steel. How much it's going to help if you're changing your structure to be built by using high, let's say ultra high strength steel? Helps nothing. And why? Because what happens is this. You just have this linear line to be longer than comparing the conventional steel. But that doesn't help you because the residual stress, again, because of the violent way you introduce in the heat to your structure, going to be again in a corner where the linear turned out to be nonlinear. Again, let me emphasize, very locally. You don't see this when you look at the entire structural behavior, but you see when you look at this in the locally. This is a big problem when you're using the high strength steel, because high strength steel, I would say that the fatigue is even bigger problem in high strength steel because it makes it possible to build the structures that are more slender, that are more lightweight, but then the dynamic loading is typically more severe than more bulky design. And that's why the risk and most of the failure modes when you're using high strength steel is based on the fatigue, particular fatigue of the welded structures. So why welding? Do we have any alternative ways to combine components? Yes, we do. We can use a gluing, we can use bolts, but they're not very affordable. It becomes to be expensive to use them. So welding is economically the most reasonable way to go. That's why. You just need to learn the way to go. All right. This is what I meant about the local high stresses, because of the local, this geometrical nonlinear, this geometrical non-smooth geometry. If you really look at how the stresses, because of the geometrical change, they are typically higher than the stresses that keep structure in a equilibrium position. And these stresses are, again, simply because of this very local detail. And these very local details are something that you need to be very careful with, because the fatigue prediction methods are based on the level of stresses you're able to get. And now if you're using multi-body models to get the stress histories, you can get the lowest possible, lowest accuracy stresses in terms of the local details. And the local details are these like equilibrium stresses, the one that keeps the structure in equilibrium position. But now, again, if you take a close look, if you make a finite element model using this kind of structural detail, and you make your finite element mesh to be very fine, close where the welded toy is located at, you will see that the stresses actually becomes to be very, very high. They will actually go almost like infinite numbers. And this is simply because of the geometrical nonlinearity you can see here. Now, based on the method you use, there is a method that I think this university is very advanced, and the Professor Timo Björk. I don't know if you have met him you haven't. He's specialized in fatigue, and they have developed a method that you can take something that is not exactly the actual stress that is going to apply in a welded toe, but very close to that. It's called hotspot stress. And this hotspot stress, you can use a more advanced, more enhanced fatigue life prediction. Or you can actually get the actual stress that is applying, and then you can use a fracture mechanics. Not easy to use because it needs a lot of parameters that sometimes are not so clear, but that's one possibility. All right, but the first thing first. First thing would be this. Okay, so once you have completed your your multi-body simulation, you get the stress history that is typically roughly the way that you can see in the top of this slide. You can have this kind of stress history could be easily coming that you first have your crane, you take a hold of the payload, and because of the static weight of the payload, your stresses will increase at this level here. And now because of the movement of your structure, there's going to be dynamic stresses. And these dynamic stresses are due to the inertia, due to the vibration, so on and so forth. And they will be superimposed to your static stresses. So this fluctuation that is damping down is due to the dynamics, due to the motion of the structure. and then you left your payload back to wherever whatever you wanted to put it, and that's where your stresses will disappear. But again, there's maybe a little bit of dynamic fluctuation, and this is going to be a typical set of the stress history. What you need to do is you need to be able to identify something that is called stress ranges. So you need to know like how many times you kind of increasing and decreasing the stress, because that's what matters in the fatigue. So if you keep your stresses high all the time, that's not going to be so risky business. That's not going to be so dangerous to you. Or if you keep it low all the time, naturally that's not going to be very dangerous. But the fluctuation, that's the highest risk you can get. So the stresses are on and off. This is something that is high risk, because what you need to identify is a range of stresses. And this range of stresses you can get by using something that is called rainflow analysis. The rainflow analysis is something that is, well, as the title implies, it's something that you make like a container using your stress history. You make like a pot, a bowl, based on your stress history. But of course, it's not going to be looking the shape of a cup, but it's having the more complicated shape. Now, what next is this? So let me see if I can make a drawing to this presentation. No, that's not possible. Why not? Yes. You're good. Okay. So this is time. This is stress. Okay. And now your stress history is looking like, let's get started here. It's like looking like this. Something like this. Okay. Rainflow analysis is something that you put, you consider these 2D graphics as a container. You put the water as much as you can to this graphical representation. So if I put the water here, so let's get started. Let's say that I get it started here. So the water level can go all the way up here. Here it can go all the way up here, 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 here. So all these is water now. All right? You with me? You understand what I'm doing here? Okay, so then what you do is that you are releasing the water off from your container, saying, okay, this is in the lowest point that I can find. So let me put here a valve. Let me drill a hole to this container. So water level will drop here to here. So this is going to be your delta sigma, your first delta sigma. And then you're going to see, hey, there's another water level here, like here. So I'm going to make a hole here to this end. Again, your water level will drop this much. That's going to be your another delta. But there is a water left here and here. So this is how you go, and you're drilling as long as there is a water left in your container. And you're making drillings as long as there is anything left. And once you're done, then every time you see that the water level is dropping, this is going to be your delta sigma. So then you can make a statistical computation. Okay, so I have a delta sigma that is a worth of, let's say, 150 megapascal, and then you compare it. This is what I was able to repeat like this many times. And the lower stress levels, delta sigmas was this much and this much. You keep on counting that. And this is how you can see that this is my overall damage, or let's say overall stress history that I can get. Now there's another formula that once you have figured out all these deltas, it's going to replace all your deltas by one single delta value, because fatigue life experiments are always carried out by using constant stress amplitude. They are never made by using this kind of variable stress amplitude, but always a constant stress amplitude. So to being able to use this experimental information, you need to convert this history that consists of small stresses and large stresses, or let's say delta stresses, by one equivalent delta stress. That's it. All right. And now this one delta could be corresponding to, let's say, hours, working days, minutes, whatever you want. And this is an information that you can use to start computing the how much fatigue you have in your structure. I mean, how much fatigue life you have left in your structure. That would be a better way to say. Now you're ready to go to fatigue analysis. But this is something that you must do. You were able to follow me. Okay, good. All right. Then you got this. You get these normal stresses, so you get this equivalent stress history. This is what we were able to compute by using the rate flow analysis and equivalent stress computation. And then if you use this stresses that you can get directly from multi-body system dynamics, then you use a method that is based on pre-calculated tables and experiments. These are like you're looking at your structure and you're comparing that to the ones that you can find from standards. And if you find them to be close to what you have under your investigation, then you have a formula to compute the fatigue life for that particular detail. And if you wanted to do something more sophisticated, you need to get more information. And if you wanted to use these hotspot stresses, then you can use a detailed finite element models or boundary element models or measurements to get the parameters that gives you more accurate estimation what exactly happens in your local detail. Or if you really want to torture yourself, not a good way to say torture yourself, but you want to have an accurate prediction, then you can use something that is called fraction mechanics. But again, you need to get the more parameters to make sure that you can accurately predict what happens in very detailed level of your crack throwing process. That's what it is. Let me show you an example. This is an example. So this is this crane that we have looked numerous times. So this is a flexible structure where there's a payload, there's a three hydraulic circuits, and each of the bodies are modeled as a flexible bodies to make sure that we can get the stresses out. All right. So that's the procedure. And now this is not very clear picture, but there is two curves here. The one that is red in a color, another one that is yellow in a color. And we are comparing how accurate is the stress history. I'm going to show the better pictures to you momentarily. But what I would like to highlight here in this slide here is this guy. You don't see this well, but this is me 100 years back. Yeah, you don't see this well, but yeah. Okay, anyways, so let me show you how are the two locations. These are the stress histories. So this is a stress. This is a typical example about how the stress look like. So this is time, and then there's measured, simulated, and then you can see two different locations. This is all about the local gain. So the fatigue is almost always a local gain. So you need to pick the locations that you're interested in. And this is what makes it difficult because, like I said, that there is so much welding in structures that you cannot take a look at all of them. You need to have your engineering sense to pick the ones that are probably the most significant ones. How? That's how you're developing your engineering sense. All right, two locations. The one that is here in this lift arm, another one is in a lift arm, but the other one, this A, is extremely harmful because you see that the stress history already here is pretty severe. So he's experiencing very heavy stresses. And when you take a close look about this, there is a very harmful design detail located exactly where there's a high stresses. And this design detail is this symbol knot, this kind of knot that is used to make sure that the hydraulic pipes can travel to this cylinder. These knots could be located anywhere you want, but unfortunately, this particular designer selected the point that is the most risk position. Why? Because this point here is loaded the highest in the entire lift arm. A lift arm is typically where the highest stresses are located at. So the worst of the worst, you put the knot. And you can put the knot because, again, it's about how to make a hydraulic pipes such that they are connected to lift arm, so they are not loosed. You can put it anywhere you want, but not the place that is highly stressed. And I'm sure you want to know what happened after that. Of course, there was a fatigue crack growing in this particular location, because you need to consider welding as your best friend and worst enemy. Best friend, because it's affordable way to do any kind of connection, including the bolt connection here. And your worst enemy, because this is where the crack is definitely located at, initial crack. And if you put your initial crack in a location where there's a high stress history, this is not going to end well. This is not going to land well. And that's exactly what happened in this case. What you could do, two choices to avoid this thing. Well, the first obvious and simple choice is take it off, put it someplace else, because again, it's like decoration, and decoration doesn't need to be the place where there are high stresses. That's one thing. Or you can, if you must, put it this place. If you have no other choice for the other reasons, then you need to use something that is a post-treatment process. You need to go and look at this particular detail very carefully and make sure that the initial crack that is located here is not going to be a problem. Hammering, TIG welding, whatever you want. Painting, not helping. Because the painting is like, it's the same thing that if you have a, not good looking wall, you paint it, it's not going to make your wall looking good. Okay. All right. So that's it. That's the end of the story. So another question. Fatigue of the welded structure can be improved by using high or ultra high strength steel, using painting or another finishing technique, using post welding treatment techniques that are removing the initial crack. All right. So Alt Tab. Yep. Yeah, that's what I'm trying to do. Like this is okay, I got 19 answers already. Oh. 19. Oh. Here. Where is this window? Is it here? Okay. God damn it, I still don't see where is this. I want to show the results. Where? Oh, there. All right. So is it gonna be or is it not? Not. What? Yeah, it will be 100% because there are 19 answers, and each one of you are following my explanations, right? No comments. Close, but still no comments. Okay, the next one is this one. Fatigue of a welded structure can be improved by, of course, in a welded structure is all about controlling the crack propagation, the crack growing. That's what matters. Because crack is growing, but not fast, slowly. All right? So then I will go and jump to the next topic because I promised to Mustafa that I need to be off at 10:30 at latest today. Okay, you guys answer this one, and I will take myself. But can I make this disappear like this? Really? I was this one. Look at that. Learning every day. Except that, I was thinking that, I don't know how it is, but I thought that in university lectures, the learning should be here to there. Not the other way around. I don't know how it is. Is it defined by the law? We all learning. So we all learning. I don't know if you guys are learning, but I do. I'm learning. All right. So everything I explained to you was all clear already. So you knew it. Okay. All right. So we continue then. What about this? I don't think that you know this story. This story, contact modeling. Like I said, contact modeling consists of two parts, where the most significant one is the contact prediction. This is what the usually is taking the most CPU power. This is something that I'm going to take an example from the games, not the recent ones, but you know that the games, you have to have a good contact modeling. I'm sure you know the rally games, where else you need the contacts. Well, I'm sure in many games, not really in the war games, not in a strip poker, but others you kind of need a little bit of contact modeling. Most of the dynamic games you have to have a dynamic modeling, and most of the developments made are coming from the game industry. Not so much about, I mean, partly from multi-body system dynamics, but this is where the multi-body system dynamics and the game industry becomes to be very close. You know that there's a lot of game engines that are not very bad, like Bullets. I don't know if you guys used any of the game engines? Hardly. All right, but anyways, they are not that bad, and some of them are based on multi-body system dynamics. Some of them are multi-body system dynamics except no constraints, because they still are struggling to deal with the constraints. So the way they do the constraints is introducing like artificial forces, but not constraint equations. That's okay. It's most of the cases is okay. What they're lacking big time is, of course, engineering components, like environmental components, typically non-existing. Deformable ground, typically non-existing. Hydraulics, definitely not existing, because who cares about hydraulics in games? No one. All right. So contact modeling. So let me show you an example. So okay, this guy is not willing to play. Why? Oh, I have the pen. No, I need to. Not such option. Arrow. Should I just click this one? No, not a good choice. So it's back, but how can I take this pen off? Oh, here. No, this is the thing that I still need to practice. Oh, I can use, no, this is still a pen. Insert pointer. I think it is this one. No. Oh, no. I think this is it. No, I want to go away. I don't want to. God damn it! It was so close. So let me put it back here. How is it streaming? Can somebody check this streaming? That is still healthy. Something wrong in this animation. Yeah, I think it was a problem in another contact. This is from the Rally game, and they're just demonstrating how good these they contact models. And look what they did. You know, some of these contact models are made in a way that, you know, this is not willing to play. They're made in a way that they can introduce damage. So it's not that you just, you know, hitting something and that's it, like typically is the case, but you can introduce some, you know, some kind of like damage to your car. And of course, they are pre-calculated damages. So it's not that you have a random contact and you can get that damage based on that, but they are pre-calculated, which is still okay. It's okay. All right. Anyways, so how is my stream? Is it still, can somebody check that it's healthy? This is visible, what I'm displaying right now. Okay. I think it should be. I think I can check it from there. Yeah, yeah, it looks good. It looks good because I can see that this is from my OBS. Yeah, exactly. All right. So, like I said, two phases, two steps to take: contact detection and contact event modeling. Hardest is a contact detection. This is that typically takes most of the time. How you can make it happen? There is a technique that is commonly accepted to be state of the art, and this is called bounding box method. And the bounding box method itself has a lot of varieties, but the concept itself is quite simple. It works in a way that you use boxes to predict where there's a possibility of contacts. And these boxes goes in a different level. You can get started from very big boxes. Again, let's think about the rally cane. So you have a big box that is big enough that you can put your rally car inside of the box. All right, that's your first box. Then you have a separate boxes depending where that you're driving in your car. There could be another box that is representing the house, and house is far off where you're driving. So let's say that is a kilometer off where you're driving at the moment. There are other boxes that are maybe closer to you. Let's say each of the trees are under the box. And now you're measuring whether or not you're close enough to big boxes that there's a possibility to collide. And if answer is yes, then you move on the more detailed level to looking at. So then you're comparing, okay, so well, I think this is a better example than the car is the crane that is used to move containers from harbor to ship and back. Now there's a big box that is big enough to put the entire this docking system, or the system that takes a hold of this container that's under the one or inside of the big box. Another big box is your ship. And now you're computing whether or not this device is close enough to the ship that there's a possibility of collide. If yes, you can move the more detailed boxes. Then inside of the big box, there are small boxes. Let's say each of the drawing details. So that's like the one that are these closing mechanisms. These are the closing mechanisms. They are under the one smaller box. Now you're comparing whether the possibility the smaller box is colliding with something that is corresponding smaller boxes in a ship. And if, again, answer is yes, you're moving the last level, which is a lift level, and the lift level is already the drawing objectives. You're looking if these drawing objectives are actually colliding, and if the answer is yes, then you're moving on to contact event modeling itself. But this is how it works. The varieties are coming because there are different ways you can put the boxes inside of your system. You can use like you see here, axis aligned bounding boxes, oriented bounding boxes. Each of them comes with certain advantages and disadvantages. But again, the concept is simple based on the boxes: bigger, medium, and smaller boxes. That's how it's behaving. And now this saves a lot of computing time, because if you think about that, there is a lot of different contact possibilities, even in this harvester crane. You need to check if each of these contact possibilities is true or false. That's going to be a lot of computing and takes all your CPU energy, and that makes no sense. That's why you're saving off a lot of CPU, because you're comparing these big objects, and if answer is no, that's where you stop. No further computing needed. All right, so this is the first step. Then comes this interesting second step. And this interesting second step is only valid when you're using undeformable models or undeformable bodies. Of course, if you have a deformable bodies, then you can get very accurate description what exactly happens in details. Like here you see that there's a gearing system. And if you have modeled this gearing system as a flexible bodies using finite element modeling, then of course you see in very detailed level what happens in your structure. But you understand that, in game technology, most of the multi-body applications, this is not possible. This is not going to be the way to go, because if you model each of these details as flexible bodies, of course you can get very accurate description what happens in a context, but your CPU need is enormous, and you're not advancing well in your simulation. That's why most of the cases you're assuming your body to be rigid. and you kind of pretend the flexibility within your rigid body. Pretend the flexibility within the rigid body. And this is something that is most of the cases what you need to do. Now you have two choices to make it happen. And these two choices are based on penalty forces or something that is on complementary approach. Penalty force is that you pretended the flexibility. That's the way that you are allowing rigid bodies to penetrate with respect to each other. And this penetration is something that you use to create the forces that are separating them from each other. So the penetration in real life, that's not going to happen. Of course, it's not going to happen. So if you have like this remote and my phone, and if I make them to collide, they don't penetrate. They don't penetrate because in real life, there are flexible bodies. So there's this surface that is bending a little bit in my phone. This surface is bending a little bit. So this is what happens in reality. But when we're modeling them, the first choice is use the penalty forces. And the penalty forces will be based on indentation, which indentation is like imaginary flexibility, that they are kind of like penetrating each other like this. And based on the amount that they are going or they are superimposed, I'm pushing them away from each other. That's how it works. This alternative, and again, when you read the stories and you hear something called smooth dynamics, that it means that the contacts are modeled by using these penalty forces because they are smooth. They are not violent, rapid things. They can be somewhat violent, but they are still like smooth dynamics. And his alternative is something that you're using inequalities. You're saying that these two bodies, they can do whatever they want, but they cannot penetrate. And this is something that you need to use completely different mathematics, which is based on this cone complementary approach. And this, when I cut the corners, I can say, okay, it's like constraint, but not the constraint we are used to deal with, but the constraint which says inequality, saying that this remote can go as far as it wants, but not crossing the boundaries of the phone. This is my inequality. You follow me? This is non-smooth because this can go anywhere it wants, and all of a sudden when it approaches here, constraint comes into play and say, okay, now you stop. And this is going to make the nature of the dynamics to be non-smooth. Comes with a certain benefit. The big benefit is that when you can really deal with a lot of contacts, I mean, the millions of particles you can deal with using this cone complementary approach, penalty forces, not really. And you can also deal with the different weight differences. There may be an example in your simulation that you're running a tank, military tank. The military tank weighs, I don't even know how much it weighs, but it's quite heavy. Is it like 50 tons or? I don't know, it's heavy. It's heavier than a passenger car. Let's say there's 40 tons. And then you're running to your tank and you're hitting the sand particle. Sand particle weighs 1 gram. Okay, 40 tons, 1 gram, the weight difference is significant. And when you're using this penalty approach, you know what's going to happen to this sand particle. When you hit the sand particle with your tank, it's going to fly far. It's going into outer space just like that. You see, that's not going to happen in reality. The sand will just go away, but it's not flying like violent way. And this is the thing that is going to be hard to deal with when you have these penalty forces. Cone complementary is better. It's still not optimal, but it's better in cases like that. All right. So penalty. Very simple concept. It's like this. You have a ball that is coming in a contact to surface, and these geometries are overlapping. Well, now based on the amount of overlapping, you're introducing another force component, pushing the ball to be away from the surface. Simple like that. But typically, you need to use a few tricks to make this happen. The first trick that you need to use is that, first of all, you need to be very careful with your time stepping. And because it's possible, particularly when you use a variable's time steps, again, let me take this remote and the phone, that there could be a remote located here. Let's say that my phone is a surface made out of the concrete. And now this penalty force is typically based on the material properties of these bodies that are overlapping. So I have here my remote, and you compute your remote to be here, here in next time step, and in a step that follows, the remote is here. So it's this much deep under the surface that is made out of the concrete or steel, let's say steel material. And I'm computing the force to push this remote away from my steel. And it is like 20 centimeters inside of my steel material. So the force that will be introduced is going to be huge. And this remote going to fly so far that I'm never going to see it anymore. So that's not going to happen in reality. So this method is somewhat sensitive to time stepping and integration settings. You need to make sure that it's able to understand that I'm getting close to the possibility of contacts and not putting excessive amounts of penalty forces. And the penalty force is supposed to be, or actually make sense if they are smooth as well. Smooth means that, the equation that you need to compute these penalty forces is very simple. There's the stiffness based on the bodies that are colliding, are in contacts, and the x is a penetration. But typically x is power something other than 1, because 1 is a bit of the problematic, because if you have 1 as an exponent of x, then this particular point where the contact just takes place is non-smooth. And this is going to be difficult integrators to understand this. So what you wanted to do instead is that you wanted to make them smooth, like n power, which is this n, is equal to 2. Now it's smooth. So your penalty forces are progressively increasing when you're getting inside of when the geometries are more and more overlapping. And this is more pleasant in a computational perspective, because here, this is smooth all the time. So though non idealities, or not idealities, but not this kind of the step that is taking you from the 0 to the increasing line. But this is progressive, so it's much more pleasant in computational perspectives. All right. So this is how it works. So it's pretty simple. So it's not too complicated to model. Very often used. Here is an example that is being used. Now, I mentioned earlier today, there's one professor, Timo Pyrk. There's another super famous professor we have in our department, Jussi Sopanen. When Jussi was young, so he made this, he's still young, but when he was younger, let's say this way, when he was younger, he made the software about bearing modeling, because his life is always about the bearing and rotating shafts, entire life. So he made a bearing model based on the multi-body system dynamics. And this was, again, based on penalty forces. Still, it was somewhat good bearing model, and it was based on the way that you compute the penetration of each of the balls with respect to the inner and outer ring. And based on that, you're able to detect how much force is imposed to each of these balls. And this study that was made at the time, the model looked like this. So it's not too complicated. Again, it's based on this simple thing. You have this stiffness. Remember, we looked at the penalty formulation earlier, so it's the stiffness. So stiffness, then the penetration, and the penetration is power 1.5 to make it more smooth. Simple like this. So of course, what is difficult is to compute these penetrations, but there is a geometry to make it happen. Now, this paper that was made long time back, if I remember correctly, is the most cited paper that I have in my career, and Jussi's career too. So we made this together, well, some years back, more than 20 years back. But anyway, so this was something that was based on the penalty formulation, and it was describing the bearing behavior. Now, using this bearing behavior, you can use introducing unidealities to your inner ring, outer ring. You can introduce different kind of pre-loading conditions and so on and so forth, and you can get the better understanding, and the faults as well. You have a better understanding how the bearings are behaving. this is a good example. You see that I have here a shaft, and there is a mass. I mean, there is just a force that is end of the shaft, and the force is constant all the time. And when you look at the reaction forces that are force at the moment, they are fluctuating all the time. Like, really? How come? Well, because the bearing behavior, because the bearing is such that sometimes the force can travel exactly through this ball. Sometimes it's traveling through the two balls. And this kind of behavior makes this a fluctuation not significant, but you see the fluctuation all the time. So it's not the constant as it is a loading here. And then, of course, different things, different kind of plays. There is it Mustafa coming already? Okay, I don't remember what was the deal about of this. But you can put the triangular inner ring, and you see, okay, this is how the forces are introduced, or a crack inner ring, and the crack is pointed by arrow. Not willing to play this video. Okay, but that's how it works. Penalty forces. Let me wrap it up. Penalty forces, simple to use. You just need to be careful with the integration settings. And it's very often used. An alternative. Contact force can be described using penalty forces. Drawback associated to this method is damping is difficult to describe. Multiple contacts are difficult to describe. Method is sensitive to integration settings. Yes, I know, but still, it is what it is. Okay. All right, so let me take a, I think I will, I'm gonna take a look at this one. All right, success rate of this. Last time it was 83, if I remember correctly. 90, 90? 89, 89, 89. I'm saying 100. You said 80, 90, 95. All right, 95. All right, one more, which is this one. Contact forces can be described using penalty forces. Drawback associated with this method is, and I'm gonna take this off. Like this. And I will continue with my story because just a few slides left. And then this is a cone complementary approach. Okay, so this is a conceptually very different. And you can change the entire equation of motion because you can look at these geometries and you can create the inequalities, like constraint equations, inequalities that are predicting or like not making possible to have this penetration. This is somewhat lengthy thing, but the story is pretty much like you can see here. This is your inequality. And that's what you're going to take into account in your equation of motion. And this is going to take your entire different mathematics. So this is still in a framework of multi-body system dynamics, but the special, definitely special feature. I want to show you one animation or one video that is funny, I think. Not this one. This is showing the simple things. Where's my pointer? Here. These balls are dropping and the conducts. Ah. Okay. These are based on the cone complementary approach. Who is really good at this is my good friend, Dan Nekrut. And I want to play a video that is made by Dan. I think this is kind of nice. So let's see how this works. This is from YouTube. Okay, so the online participants are saying that they hear nothing from this video because I'm guessing the way that I'm sharing this. Okay, this video is not going to be too lengthy. So the online participants, you can be off because this is going to be the last thing we're going to do. You can take a look at this later. We're going to take a look at this animation, this video, and then that's it. That's it. Okay, what I will do, you guys, I'm going to send you a link so you can take a look at this later. So this is about many-body. This is what terminology that was kind of like developed by this Professor Dan Nickward. The many-body means that you have a lot of possible bodies that can collide. That's what it is. And when I'm saying a lot, I'm thinking about millions of possibilities. This is something that you cannot deal with this smooth dynamics. It's not just computationally possible. This too is a computationally intensive, but keeps the promise that one of these days you can even run these in real time. I don't know, one of these days, let's say somewhere in the future, you can run these in real time. All right, we'll provide you a link. So I promise you today that next week I will give you a list of questions. I will give you a link to this animation. So take a look at that. What else I promised? Exam. 3 promises. So what else? Was there something else? Yeah, the exam days. Okay, all right. This I don't get at this exam. So why you are not able to see it? Because we made up a lot of work, heavy work to make sure that you can see the exam results. And now you don't see it. I think that I need to ask Suraj. He knows this. All right, guys. So we're gonna close for the day, and I will send a link. Make sure that you have a list of questions. That's gonna be next week, Wednesday, and that you can have an access to your results. Thanks, guys. And let me see. The last thing is take myself here, and I stop streaming. Oh, hold on. Don't go yet. Don't go yet. This one. So how much? What's the success rate here? This, by the way, is really nice. I don't need to put this on and off all the time, so I can use the same settings all the time. Good that I figured this out. Or was it me? Maybe it wasn't even me. So Mustafa, I know how to deal with this now. I can give you a lecture. This how to deal with this. This settings, now the settings are best ever. All right. The contact force is the success rate 76. Not bad. Not 100, but not bad. All right. See you guys next week. Next week it's gonna be biomechanics, and then something that is right, wrapping up all my knowledge to you. Okay. So I'm gonna take this one. Seems that I'm in the wrong screen or something.